I want to talk about today is PCB design. So I want to talk to you now about it, because possibly if you're in capstone, you'll have to design a PCB board. These can be hard things, these can be easy things. If you look at some of the boards my embedded system students are doing, people have gone crazy and added lithium-ion battery chargers, they've added Bluetooth modules, so you can have really crazy PCBs. You can also have really simple PCBs where you're just soldering in basic resistors and dip circuits to connect things up. It really depends on what you want to do with your design, how complicated you want to make it, and sort of what your objectives are. The fundamentals, though, is that a PCB, a printed circuit board, is created from two things. It's created from an electrical schematic, and it's created from a layout. So the electrical schematic says, these are all of my parts, these are all the pins or all the ports on my parts, and this is how they're connected. So it's a completely logical description of what your board is going to be. Like A connects to B, connects to C. The layout is determined by how you physically route all those wires. So the second half is a board layout. And a board layout says, well, you have all these components, they have some physical size, and you have to tell me where these wires go. So you have to physically lay the wires on the board to route the signals around. So the schematic is the number of components, the size of their component, the size of its implied. The layout is physically where they go. Generally, you manually route all of the layout, and you do it because auto routers are stupid. We'll look at auto routers in an assignment and see how they work. The board can have multiple layers. So there can be a top layer, a middle layer, a bottom layer. So you can sort of have like 3 floors to route your signals through. So in a nutshell, PCB design is a schematic and it's a layout. Who's done some PCB design like on co-op or whatnot? Okay, so a couple people have done. What tools did you use?
I used Cadence Allegro.
Okay, Cadence. Michael. Okay. Eagle. So people use Eagle, they use KiCad, they use Cadence. I find that all the tools are terrible, but they all have various positives and negatives. So this is my note here. Overall, the theory is simple, but the practice is really bad. The practice is really bad is because you have to make logical things work instead of A connect to B, but then you also have to have physical things connect. Like it has to be of a certain size and a certain width, and because you have to physically solder the components down on the board. So the major tool that people use is Eagle, and Eagle a couple years ago was bought by Autodesk, so there are kind of a couple different versions of Eagle floating around. Anyone will kind of do it for your basic design. The important thing to note is that you can logically put whatever you want in your schematic, but all of those elements have a physical size. So when someone's going to design this circuit board for this accelerometer that you're using, like, it's only 6 components. It's really simple to logically put together in a schematic, but then they have to physically place everything on the board. 1, to try to minimize size, but 2, to minimize that you can actually place everything together. You can make your parts as small as you want on your PCB. You can make resistors like the regular dip resistors that you have, or you can make them the size of grains of sand. Now, I would never do that because they become unsolderable. So you can have super, super small parts, but it may be impossible for you to solder, and those may be machine-only parts. This is what a schematic looks like, and this is a schematic of one of the Arduino boards. And so what this shows you here is that this is a particular chip that is in the schematic. This is the Atmel 328P. And these are some of the couple things that are connected to it. And you can see that there are 3 LEDs with some resistors connected to these pins right here. Some of the analog input pins are broken out into a header. This is what this schematic is trying to show you. A couple things about the schematic. The size of the picture on the schematic means nothing. So here, this chip is laid out with pin 1 here, and pin 2, 3, 4, 5, 6 over here. They're not physically like that on the chip. Like, that is not physically how the pins are laid out on any of these chips. It's laid out that way logically logically because it's grouped for you to help route things together. And the way that this is that like here are all of the port C pins. Well, let's just put them close together logically so we can route them out to a header. At the same time, this symbol does not tell you how big that processor is. If you can read on the diagram, it says that it's a DIP processor, which means it's a dual inline package, which means it's your regular, if you remember the little ICs from EC220, just snap into the breadboard, that's a DIP package. So this is an old Arduino with a big DIP package. You can also get it in various surface mount packages, which makes it the size of like a fingernail. This schematic visually does not tell you what pin package it is. You'll have to dig into the particular part that's selected, and you'll have to read what pin package it is. So this says nothing about the physical layout of the board. It says everything about its logical connections. It does not tell you anything about size. How you sort of get to that notion of size is that when you pick a part, you're going to pick a part with a certain surface, or you're going to pick a part with a certain pin package. Chips are manufactured in a variety of pin packages because some people want through-hole components like the ones on the right. Some people want surface mount components with little sort of flanges on them for the pins. And some people don't want any leads or anything, and they're tucked away underneath the package. So a part may be manufactured in 3 or 4 different pin packages. Those packages may have more or less pins because it's easier to put more pins around this package than it is around this package. These pins take up a lot of space. So you can't have a 40-pin DIP. It's going to be tremendously long, whereas you could very easily have a 40-pin SOIC. So when I say through-hole, I'm talking about your classic resistors, your classic ICs, things that you can snap into a breadboard. Through-holes are really easy to use. It's what you're familiar with. But I'll be honest with you that if you make a design with that, you're actually going to have a worse time. It really is a worse time to use through-hole components because it's gotten to the point where the surface mount stuff can be pretty easy to just solder and paste on. So what my students do in 420 is that we take the solder mask, you take your board, you put a nice little stencil over top of it, you smear paste on it, and then you sit in the back of the room like Ashley was doing and put all your boards on your PCB. Is that what you're up to?
I haven't put the smart on it.
Can I steal your board? Is it movable?
Yeah.
Alright, let me see. Give us your board, please. Yeah. Okay. So this is Ashleen's board right here, and you can see sort of this is what gets made out of the PCB design, and there are no holes on here except for these kind of through holes on the side. And those are used for headers because we're debugging this chip. But what she's going to do is she's going to stick this little stencil mask on it, which has the exact same cutout as all these pads. And so she sticks the stencil over top of the board and then takes solder paste and smears it. It'll fall exactly where the pads are. And then you just get some tweezers and put your pins down. It's honestly a lot easier to do, thank you. It's honestly a lot easier to do than if she ordered that as a bunch of through-hole packages. The board would probably be about 3 times the size, and honestly, this is an accelerometer. You're not going to get it in a through-hole package. Like some parts will not come in a through-hole package. So when you've got the choice between the two, it can be tempting to sort of do this because you can just snap boards in. That's fine, but also understand that this is not necessarily as difficult either. I am not the world's greatest fan of PCB design, but I am converted to this because it is still easier overall to get done. When you're talking about pin packages, your schematic can look any way, but that, again, does not imply necessarily what package you're working with. So this, for this ATmega, is a QFN package, which means that it has very small sort of leads attached to it. This is the same device, but this is with a sort of a TQFN package, so the leads are a little bit more exposed. So my point here is that if you look at the schematic symbol, you don't really know, am I dealing with this chip or this chip? And that matters when you go to the layout and you have to route things, and it matters when you go to actually fabricate it, and you have to put the solder down and connect everything together. Same thing with a resistor. On the schematic, a resistor can look like this, it can look like this. That can either imply a through-hole part, or it can imply a surface mount part. So if you see these symbols on a layout, these are drill holes or these are vias. So that green symbol means someone's drilling through the board, there's a hole there, that hole is there to connect to different layers, or it can be actually just a drill hole. This is a little tiny resistor with pin pads on either side. So, a particular chip may have multiple packages, but the symbol looks exactly the same. Make sure that when you pick a object from whatever tool, whatever library you're using, you get the one with the correct package. It matters for routing. It matters when you go to DigiKey and you order the same part. With the students here, with them ordering all of their Atmel 32U4s, there are 3 or 4 different package types. If they just type in 32U4 and order a bunch of them, they can get chips that just don't work or don't fit. Make sure that when you're placing things that it's not too small a package where you physically can't handle it, or you physically can't get the solder between the different pads to make sure that they're connected. Couple other packages, sort of a logic gate array, different pins. You can have sort of different configurations of your different devices. This is a little temperature sensor that we're going to use. If you're going to order it, you can order it in its dip or through-hole package. You can also order it in your surface mount package. And everything is going to be slightly different, and you can look it up. But everybody's got some sort of package for their parts. Now, when you are doing the schematic, when you're connecting up your design, you are establishing nets. You are establishing nets between ports on devices. A net is a logical connection. It does not actually say where that wire should go. One funny bug in Eagle is that there's a net tool and a wire tool, and they look exactly the same. But if you use a wire tool, you're actually drawing a wire on the schematic, which is bad, whereas a net is making a logical connection. And the reason that you use a net is that you can say go from this pin to this pin, but you can also label the net, and that everywhere you have a net of that label, it will be logically connected. So this is the header programmer for Atmel. This is the ISP programmer, and this is connected to the MISO line on the SPI interface. You'll notice that there isn't a line here running all the way back over to the processor, because that would make a really ugly schematic. It wouldn't work out. But if you make a net and you name the net MISO, and then on your Arduino or whatever your board is, you make another net and you name it MISO, in the layout, they will get logically connected. So you don't have to draw wires everywhere, but you can just give a net a name, and then when it comes to placement, they'll be connected. This is going to be connected to power, and this is going to be connected to power, but you don't see a wire running to the output of the power supply. That will happen automatically when you go through the layout. One thing that you want to run through is an electrical rule check. So that checks the schematic to make sure that you have connected everything up properly. And properly only means electrically. So it's going to make sure that you don't have outputs connected to each other, or input or power connected to ground. An electrical rule check is just going to check if you've left things disconnected, if you've left things floating, or if you've connected pins that shouldn't be connected. Sometimes you want to do that. A lot of times it's going to give you an error saying, oh, the output of your power supply is connected to the output of your processor that's VCC. And yes, that's fine, because the output of my power supply should go to the VCC line on my processor. So you can, if you get an error, it's like having a warning in a compiler. Like, you probably should fix it, but if you know what you're doing, it'll be okay. So you can get electrical rule checks, but you can approve them, and you can wash them away. One thing you do want to check warnings for is stuff like this. So what you want to ask yourself, are these wires actually connected? So these wires in the diagram are not actually connected, even though they overlap, because there is not a node here. So when nets are connected, you'll get a little green dot, you'll get a little green node, and what will happen is you'll go to wire it up, and you'll say, oh, I have these warnings, it's not connected. And you'll visibly look at your diagram and say, well, that looks connected. But if you drag one net away from the other, they'll rip apart because they are only overlapping. They are not actually connected. So here's an example of this. That was my diagram for here, and it said that I had a misconnected net here. I thought I was connecting the output of my power supply to VCC. But when I take the VCC symbol and I pull it away, my net should stretch and follow me, but it actually ripped the net away because it wasn't actually connected. So if lines are actually connected, there needs to be sort of a junction here. So one trick is once you've wired up all of your schematics, grab a part that's in the schematic and just sort of jiggle it. And make sure that all of the parts and all the nets move with you. If it moves free of some of the nets, then that means that they're not actually connected. At the same time here, as I said, you might get warnings on the electrical rule check about pins of different types being connected. So what the error is here is that an output net and a supply net are being connected. And it says, well, that's not good, they're of different types. However, you know what you're doing here by attaching the output of the power regulator to the supply pin, which is VDD or VCC. So you will get the warnings. The warnings are helpful, but sometimes you need to read them and interpret them to make sure they're what you want. Questions so far? Now, that's putting the schematics together. That's honestly probably the easy part of putting all your components down, saying what's connected to what. You can basically look at your breadboard that you've made in your system and copy all of the connections. So everywhere there's a wire on your breadboard, there's going to be a net in your schematic. Once you've done the schematic, you need to do the layout. And the layout is where you physically place all of the components. It's important to make the design small. As small as reasonably possible for a couple reasons. One, the bigger a board is, the more it costs. So generally a fab will charge you per area. So why make a 4-inch square board when you just as easily make a 2-inch square board half the price? But don't make it so small that you have to use tweezers and hold your breath while assembling it, because otherwise you'll misplace something. So make it small, but make it reasonably so. The other thing you've got to decide is how many layers you want in a board. The cheap basic default is a 2-layer board, meaning there's one layer of copper and then another layer of copper, and you can route signals on either layer. You can pay a little bit more, get a 4-layer board, or you can be super pro and have like a 10-layer board. Why would I want a board with more layers? Like, what is more layers going to do for me? Jason? Right, so the more layers that you've got, it's like the more lanes on a highway. You've got more space to send people. Like you can send more traffic through more easily. If you've got a 2-layer board, generally they make a bottom layer ground, because everything's got a ground connection. But then that leaves one layer where you have to route all of your signals and all of your power. And these lines cannot intersect because they're all on the same layer. It's like playing Snake. Like you can't move back and hit yourself. If you've got 4 layers, well then now you've got yourself a whole ground layer, you've got yourself a whole power layer, and now you've got 2 layers where you can put random signals all through it. 10 layers, and you're really doing something crazy, because if you really need a 10-layer board, then you've got a lot of stuff going on. And you look on your board, there's a couple things that are going on. All your boards are usually some nice black or green, or if you get it from OSH part, this nice purple color. That is the solder mask. So that is the color of the board, and that chemical, that liquid that they put on there, that paint, makes the solder adhere to the pads. So it's phobic to solder, and so the solder ends up going onto the pads. So all of this black on here is the solder mask. All of the white is the silk screen. So all of the nice little printing that's on your boards that tells you where pins are, that's just the silk screen. That's just pasted on. And the silk screen is nice because you wonder if you've got 37 resistors on your board, you should label each one so when you're putting it down, you can remember which each one is. Inside of the board, so if you kind of look at the board horizontally, you can start to see some of the other layers where the copper might be. And depending on the board, you may or may not be able to see it. But there's basically fiberglass and FR and just other junk insulated material that's in the middle between layers of copper. So your substrate is what physically holds the board together. So the solder mask, the substrate, the copper, they have no sort of structural integrity. You've got a lot of junk in the board that holds it together and acts as an insulator. This is what layout looks like. So let's say that you made a schematic and you go, whoopee, I connected all my parts together. Let me go do the layout. That'll be easy. And then the tool's going to dump you something like this. Here's already shaking your head. So you have nightmares with this.
Yes, rat's nest.
Rat's nest of wires, yes. So the layout tool has no notion of where these parts belong because your schematic gives no indication of where they physically belong. It stuns me that no one has solved this problem because when you do FPGAs, there are placement algorithms. But whatever. The fact that it's just going to randomly drop my processor and my power jack and then this in the middle here, the challenge with this is that you have to now, it's a giant game of blocks. You have to lay out these parts in an area such that they're close to one another, but that then when you route them, all the lines don't overlap. So let's say that I'm trying to connect this pin, this net from here to here, and here to here. I can't do that on the same layer because my nets will intersect. So what that means is I've got to send one of those wires down to another layer. So this layer, this might be on layer 1, this might be on layer 2. But if this is on layer 2, that means that this wire's got to be on layer 1 because they intersect. And you can see sort of what kind of a cascading problem you get. Trying to route all your devices. The advice I can give is that if you look at a well-made board, its layout is logical. So the power supply is near where power comes in. The processor is near its clock. All of the analog pins run in a row out to one another. If you look at, you can't see the layers in this one. But if you look at a board, all the pins are going to kind of flow in parallel. You're going to have logical routing to your power and ground. My advice is to place the components where they should be physically and then kind of make the routing work. So one thing you can see is this is a header. That header that we had that exposed all of the analog pins, this is that connection right there. So if we go back to here, this header right here is that connection. So it's these 6 lines, it's those 6 lines out to that header. If in the layout, it really doesn't make any sense to have this device with so many connections strung out all the way here past all these components. At the same time, it also does not make any sense to have this header on the other side of the board because all of these nets would have to get routed underneath the chip and through all these holes. One thing to note is where this green circle is, that means there's a drill hole. That means that there's a via or a hole through the board, and you don't want your wires to get super close to those holes because a drill is going to come through and bang out a hole in your chip. And if your wire's there and it cuts your trace, it doesn't care. So don't think that you can just naturally turn these wires around 180 and run them through the chip. So this has a lot of connections to this side of the chip. I would take this and I would put it right there. That's where it should go. Your programmer, a lot of the connections are over here with one or two on the other side. Maybe you can route them down over here. Like, find channels for all of the nets to go. Put your power regulator near where power comes in. Put your oscillator near the processor. Your oscillator can be subject to interference. You don't want the thing that drives your entire processor to go crazy. Keep it near the chip. And at the same time, if you have long analog runs, be wary of that. You kind of want to keep them together. You don't want them too far away. There are 100 different heuristics on how to lay out a board. At certain frequency, right angles become antennas, and they become radios, and they radiate, and you get noise. Sometimes you have to put ground planes on your analog components. You don't want your digital and analog devices to be on the same ground plane because they could have crosstalk, they could have ground loops. There's a million different heuristics because this starts to become an analog problem. So I'm an engineer, I like digital things, I don't like analog things. But this truly becomes an analog problem because of all the electrical signal going on here. If you're building a little microprocessor and it's operating at 5, 10 hertz, wouldn't really worry about it, but once you start to get up into the gigahertz range, or once you do anything with the radio, now you have an analog problem. So if you've got a little Bluetooth built-in board, like Schmidt has back there, the antenna has to be of a certain shape for it to be a receiver on the board. When I was talking about different layers, in Eagle, layer 1 is red, layer 2 is blue. It's pretty easy to see. So if you've ever opened up a schematic and you see a bunch of red and blue lines, this is what it is showing you. And what you've got here is, this is a single layer for, this is an LIS 302. This is another sort of accelerometer, and you can see the different routings there on a single layer. This is the back or the bottom of the board. So if you wanted to put the chip on the bottom, it can go on the back side of the board. There is routing done in this layer, and the remainder of this layer you see is solid blue, is because that all gets connected to ground. So usually the bottom layer, you can route on it, and then everywhere else in that layer that's not connected, it gets filled in with a copper core, and that becomes ground. And it isolates components, but it also gives you lots of ground connections. So if this big blue area here is ground, and these are my 2 ground pins, I just go boom, and dump them down to the ground pin of the board. It's like on a car where like the frame is ground, and that's what you're connected to. So you can have an easy ground point everywhere. It's the same thing here where you just have a pour, and that becomes your ground. Ground.
Why is layer 2 layer 16?
So that is the layer number assigned in Eagle. Everything on the board is given a layer number in Eagle. So I'm just going to say it's a 2-layer board. There's layer 1, there's layer 2. But if you pulled up Eagle and wanted to show this layer, it's layer number 16. Pat?
Just because 16 layers, layer 1 being on top, 16 being all the way on the outside of the board. So you just have no layers in between the 2.
Yeah, it's just the 2. Like in the silk mask is, the silk screen's what, 40 or 50 layer?
It's something really,
Yeah.
like hundreds of different layers in each.
Right, there's a bunch of different layers, and so when you go to the manufacturer, they got to understand what layers are. Like the silk screen's made like layer 50. Why is it layer 50? I don't know, there's probably some rationale. But it's just on a different layer. So yes, so this is a layer 1 placement, this is a layer 16 placement, which is essentially the bottom of the board. Again, if you're doing 2-layer design, you can do a through-hole, you can buy all those little resistors, and you can solder them in, but again, a through-hole design is going to be more complicated. What a through-hole design is going to do, though, is it's going to drill a hole, and it's going to make a via, and you're going to have all these little vias across your board. So if you've ever wondered what those like little magical holes in your board are, those are electrical drill holes. So if it's a through-hole component, it is drilled all the way through the board so you can solder it on the other side. If it's just dropping a signal from one layer to the next, it's a via such that here is a signal that is coming up from another layer and then ending up on this layer. This signal is already on this layer and is using the through hole to go down to another layer. It's like an elevator for signals. But it does cause a hole. It is a smaller hole than a through hole component, but it is sort of an electrical hole. Now, with the PCB mill that we've got in the back, a nice nifty toy, it will drill all the holes for you, but it will not automatically electrically plate them. So it is really a drill, and they fill the hole with copper. So that makes sure that the layers actually get connected. That guy can't do that. So we actually have little rivets that you pop, 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 pop into all the vias, and that's how it makes the electrical connection. I wonder if we have any vias on these boards. Questions on this so far? So, a couple comments on vias. You generally want as few as possible. That means there's less holes in the board. It's a less complicated routing. For a high-speed signal, and high speed is sort of whatever you want to make it, megahertz, gigahertz, actually having the signal go down a hole and out screws with its ability, so it can distort the waveforms of high-frequency signals. So I would generally avoid vias for anything over a couple megahertz. Actually, I wouldn't put any high-frequency signal on a via because it's going to induce some resistance and it's going to mess with the signal. You can't, as we saw, you can't put vias near other holes because it's physically drilled out and you don't want your two drill holes to collide. And the neat little tool is if you're routing in Eagle and you're dragging, and you click the nice little center mouse button, it'll automatically insert a via and drop you to the other layer. Very nice. You kind of just start dragging lines. Click, dip, click, go around. Routing. So the major thing that you're doing in the layout is you're routing where all of your signals go. And routing is a geometry problem. It's how do I get these signals from one point to the other without colliding? In general, on high-speed things, you want to avoid right angles. And I look back at some embedded system student work from a couple years ago, and I think they took me literally because all of their traces were kind of like schmooey like this. That's not really what I meant. But just if it's a high-speed signal, a right angle can be an antenna. And you don't want that to happen if it's sort of above 1 megahertz. If it's a little GPIO pin that you're turning a light on and off, it doesn't matter. But a right angle can radiate. Once you get up into the multi-megahertz and gigahertz range, you are now dealing with an analog device, and it is a dark art. Distributing a clock signal among a actual CPU or among a big board is still art. It is not necessarily engineering. You should have separate ground planes, if possible, for your analog and your digital devices. So if you've got an ADC converter and then you've got some other SPI device, you should keep those things separate so the noise from one doesn't influence the other. So if your ADC is rapidly acquiring, the noise from that operation, maybe that ends up on the SPI clock line, and then that distorts your SPI clock. So if possible, have separate powers for analog and digital, and have separate grounds for analog and digital. That doesn't mean that you have to have two power supplies. That means that there's one rail that comes off the power supply that's called digital power, and there's another rail that comes off the power supply that's analog power. That doesn't mean that you have two different ground ports, you just have two different ground lines, and they all meet back together at the battery or at the power supply. As we saw in the picture back here, you can take your bottom layer, and after you've routed everything to it, you can make a ground core and fill in it all and make it ground. It keeps things electrically quiet, and it makes the routing a little bit easier. Now, this is every student's favorite friend, the auto router. So the auto router will take your crappy, terrible design and do magic on it and automatically route all of the signals. it's 90% done. So it's going to put vias in places it thinks it needs vias. It's going to route signals around each other. I would avoid generally using the auto router. So you should manually route the signal, the data, and the power. And then if there's something left, you can try the auto router. You don't have to accept its solution. You can always reject it. So people like it. They click auto route. It gets done. It will give you a solution. The solution may be terrible, and it may not be good, but it will give you a solution. On the schematic side, we have an electrical rule check. Here on the layout side, we have a design rule check. So the electrical rule check is making sure you didn't short power and ground, making sure that things were connected, making sure that you were logically correct. A design rule check is going to check the physicality of your device. Are you going to drill over your nets? Are your wires too close together that they can't be separated? Is some of your design outside of the dimensions of the board? There's nothing in the tool that prevents you from putting components outside the space of your board. So there's going to be a dimension line. There's going to be a dimension line, and that is where the mill at the fab is going to cut your board. And if your wires are too close to the dimension line, your wires are going to get cut. And they're just going to be disconnected. So any design for any fabrication house is going to give you rules on drill size, on clearance, on different things that matter. So, for example, these are the design rules for OSH Park. They can tell you that you can have 6 mils between your traces. The traces can be 6 mils wide. The drill size is 10 mils, and you can have a 5 mil sort of ring on your traces. If you do the 4-layer boards, you get a little more clearance on the traces and a little more clearance, or a little thinner widths. So if you buy a better board, if you're paying more, they can be more accurate, is generally the idea. But a 4-layer board is going to be double sort of the cost. It's going to be double sort of the cost of a 2-layer board. Flip that, reverse it. A 4-layer board is double the cost of a 2-layer board. So, for example here, this is OSH Park. This is what I use, what I ordered the embedded students' boards on. You can see you pay per square inch and you pay per time. So in general, you're going to pay $5 a square inch for their basic service, and it's going to take 2 calendar weeks to get it to you. You're only paying $5. So a lot of their boards were $10, $15 bucks. Pretty nice because they had about 2-3 square inches. You get 3 boards because it's not really worth their time to just make one. I mean, if they're cutting one board, they're going to just give you 3. And you want 3 because likely you're going to break something, or something's going to mess up, or you're going to solder it bad. So always order in sort of duplicate or triplicate. If you want it faster, if you want it in 1 week, 5 business days, you double the price. They also have some different ones that are a little bit cheaper, that if you have a lot of boards that are really big and you're willing to wait 3-4 weeks for it, they'll send it off to China and give you a medium run and have it real cheap. And these are the prices down here. These are the prices for the 4-layer boards. So the stuff you get back looks like this. It's kind of nice. This is one of the through-hole designs. You can see where a couple students, this is from last year, not this year, a couple students have labeled their resistors so they know which ones go where. They've also put a nice little note on the bottom that says this is the bottom, so they don't forget, and they start. Because this student did through-hole design, it doesn't really matter whether your chip gets soldered in here or here, except it will be completely inverted. And all of your things will be flipped and disconnected. Other fun things that happen is, what happened on this board? No, these are just the pads. These are just the pads and the silk masks, so you can look at the different connections. So it's going to make this copper, and then where those through holes are, it's going to go, and it's going to drill through and make your through holes. And you can see the ground cores, what they've generally done. So you can see all the traces here, and everything outside of the trace has been poured to ground or been poured to power. This is okay. It's really not good that they've got the routing here between the pins. This routing must have been clearly done by the auto router because this pin is going underneath the entire chip directly over here. It would have been better to take this chip, rotate it, put it nearby. This is not really a space efficient design, but I think the student didn't really care. Assembly. So you can put together your board however you want. If you've got a bunch of through-hole components, you just sit in the back there with a soldering iron, you heat it up, you solder it like you've always done. If you have surface mount components, if the pins are big enough and wide enough, you can actually kind of put some paste down yourself and kind of hand solder them, or you can use a hot gun and you can just kind of put some paste down, put your part on it, hit it with a hair dryer, and there it goes. I think the better way to do it is to take your board, and as we saw with Ashleen's, lay it down here in sort of the jig, and then put the stencil over top of it. And so you'll take the stencil, you'll tape it down over top, you'll take the solder paste, which is not drugs, it's solder paste. I don't know why they give you a needle. It's got a needle. And you just place the solder on the board, and then you smear it across. And they give you handy little official smearing tools. So not only do they give you something that looks like heroin and something you can cut your drugs with, it looks bad. So you've got an official fake credit card where you can smear all of your stuff. You've got your liquid solder, and then you put it in the toaster oven. Well, yeah, the pizza. This is why I wrote very large on that toaster oven, no food. Because it's just been full of student boards over the years. You can use just a basic toaster oven and turn it up temperature, down temperature, and it'll work. We do have a really nice toaster oven that will get working. It's not that hard of a process, but the thing is like, look at all these components. Like, if you shift this board like a millimeter to the left, you're going to smear everything and nothing's going to land. So you have to really tape this down and make sure that when you put the paste on, it ends up where it's supposed to. And if it doesn't, wipe it off, do it again. Because you don't want to place the paste, have it smeared, and have all of your components short. So the solder mask will make the solder kind of bubble up on the pad, but if you put a ton of stuff on there, it's still going to overflow. There's not going to be enough surface tension to hold it there. So this is a hugely complex design. There's a lot of components on that design. Yours wouldn't be that complicated. So who may have to make PCBs for capstone? Jason, you're going to have to do this at some point. Karen, Ben? All right. So a couple things you can do is for your first run, if you've got discrete through-hole components, you can just drop them into the board. So you can just make, a very cheap, easy way to do this is if you're working with this chip and you want to make a PCB just so it's all physically laid out the same, just make two rows of dip through holes and just boom, stick this in and solder it. Yes, it's going to be fat, yes, it's going to be big, but you're going to have everything snapped into your board so you can test it out. Once the board's up and running, you can then take this design, take all of your other designs, dissolve them into the same board. But an easy first approximation is to take your existing components, snap them into the board, and there you go. A lot of things that you can buy on smartphone, ad-free, things like that, come with the schematic, come with the layout. So you can just take the schematic, import it into your schematic, and connect it up. The one thing I would do is that if you're doing that is always pay attention to the power lines and any sort of analog lines, because people design those intentionally. I got a lot of fun links at the end here, videos from SparkFun, tutorials. You can watch people who have more patience than I assemble these things. We will have a small assignment on PCB design probably after your exam. I just want to make sure that you can do it. It's next to things Eagle. It's really one of these things that it's not really that hard. It just takes a lot of patience to do it, and you've got to have the right tools. So you can use KiCad, you can use Eagle, you can use kind of whatever you want. They'll all basically generate the same thing. The main frustration is going to be is that if you have picked a tool and it doesn't have the part you want, and then you have to go create the part. So not only do you have to lay it out logically, you've got to lay it out physically, and that becomes buckets of fun. So not a hard thing. Take your time. It's tedious. You've got a schematic. You've got a layout. The schematic is the logical connections. The layout is physically how those things are routed. It's through-hole components that you can solder on like you're used to. It's surface mount components where you put some paste on the board, use a heat gun, use a toaster, put them down. This is the end of the exam 2 material. So who'll be on exam 2? So this is the end of the stuff in the exam. So if your exam's in a week, you have a week to study. You also have a week or like 5 days to each your lab too, though. So question, Jason? Or you just go on my week? Yeah, a little 22. So we've got a good hour and a half remaining. What you should drive at today is getting that who am I functionality ready on the spot. So do all the configuration of all your devices, run through the register tab, make sure everything's connected, and then try to talk to the device. You can modify the class, you can hack it so it does different things. You can change the main file. You can do whatever you want. But try to make sure you're getting good data out from your system. If you get really stuck, we have a logic analyzer. You can check to see if you're generating a clock signal. You can take a multimeter and check to make sure that you're lowering the chip select line. If you never actually lower the chip select line, nothing ever happens. So a couple tests you can do. But this ends sort of what we've got on that exam. So it'll be the UART, it'll be SPI, and it'll be PCB design.